How does fast Fourier transform, FFT, analysis work? Imagine trying to understand a complex song by listening to it. The fast Fourier transform helps break down that song into individual notes and sounds. It is a powerful tool in electrical engineering used to analyze signals quickly and accurately. The process starts with sampling a continuous signal at a fixed rate. Think of it like taking snapshots of a moving object at regular intervals. These snapshots create a sequence of data points, called samples, which representing the original signal over a certain period. The number of samples taken is called the block length. Larger blocks give finer detail but take more time to process. Once the data is collected, the FFT algorithm steps in. It transforms the time-based samples into a frequency-based view. Instead of seeing how the signal changes over time, you see what frequencies are present and how strong they are. This is called converting from the time domain to the frequency domain. The magic of the FFT lies in how it speeds up this process. Calculating the discrete Fourier transform directly takes a lot of calculations, especially with many samples. The FFT reduces this from a process that could take thousands of steps to one that only takes a few hundred, making real-time analysis possible. It does this by breaking the problem into smaller parts, exploiting patterns and symmetries in the math. This divide-and-conquer approach is what makes FFT so fast. Key factors that influence FFT analysis include the sampling frequency, which limits the highest frequency you can analyze. This limit is called the Nyquist frequency, which is half the sampling rate. If you try to analyze frequencies above this, you get aliasing, where high frequencies appear as lower ones. The windowing process is also important. It involves applying a special function to the data before transforming it, reducing errors caused by abrupt edges in the data block. The output from the FFT is a complex spectrum, meaning it contains both amplitude and phase information for each frequency bin. From this, you can derive the power spectrum, showing how much energy each frequency carries, or the magnitude spectrum, which shows the strength of each frequency component. Electrical engineers use FFT analysis in many ways. They analyze electrical signals to find harmonic distortions or noise. It helps in fault detection in machinery by examining vibration signals. In audio engineering, it characterizes sound signals for better quality. Communication systems use FFT to analyze modulation and channel effects. It also plays a role in designing filters and identifying system responses. In essence, FFT analysis turns a complicated time-based signal into a clear picture of its frequency content. This transformation allows engineers to understand, troubleshoot, and improve systems that relying on signals and controls. It is a fundamental technique that makes modern digital signal processing possible and efficient.